So yeah, the topic of my presentation is evapotranspiration and using thermal infrared to estimate evapotranspiration. I always like to link data and methods with an application, a real world application. And since I'm an agronomist, I would say the two main areas thermal infrared is used is in drought monitoring, which I'll talk about today, and also irrigation management, which I know less about, but am happy to answer questions about. Uh, Here or through email in the future. Let me see if I can put on my pointer. Yes, okay. So the motivation of this presentation is this ESA project here, which I provide the QR code for, called High Relief. Zoltan, I believe, gave a presentation in the morning. I don't know if he's there, but he's the ESA manager for this project. And so he can answer more questions about it if you have. So it's quite an extensive team, also including Agnieszka. Um, and we're basically trying to use the EcoStress technical workflow, namely to estimate ET and ESI, the evaporative stress index, which I will talk about, and replacing multispectral broadband vegetation indices, namely NDVI and EVI, with hyperspectral data from Prisma and Nmap. So we're trying to see if we can improve ET estimates using a combination of both thermal and hyperspectral. Uh, Martin, I saw his presentation, the one he just gave, really nice presentation. He actually, I believe, worked in the same study area collecting land surface uh, temperature data in Kapiti Ranch, which is where we're working. It's in Machakos County in Kenya. It's a typical dryland area in Africa. So yeah, nice to see synergies and potential collaborations. So a brief outline of the presentation. First of all, I'd like to talk about drought monitoring, and why we look at evapotranspiration for this application. And then this leads to a very quick introduction to EcoStress. I'm sure most of you already know. EcoStress has been used to develop these ET and ESI products for drought monitoring applications. And then that begs the question, why do we use land surface temperature? What is its link to evapotranspiration? So in order to do that, I kind of zoom out and talk about the surface energy balance, where land surface temperature fits into the energy balance, and then how we use that information to estimate ET in the main approach, which is what we call the energy balance approach. But we also have to talk about the non-thermal methods, what I call the vegetation index methods, and that's because in reality, this is what EcoStress uses. It doesn't use the standard energy balance models, which have been developed with land surface temperature. It uses kind of a different method. But I think it's important if you want to understand the bulk of where evapotranspiration research and modeling is going, it's in this first approach. And we can also see that the Europeans are taking on this approach for their own EcoStress website, which I'll talk about. And then I'll just provide some concluding remarks. So there are many ways to define drought, and I'm using this definition here just to orient you in terms of evapotranspiration. So in this definition, there's some kind of precipitation or temperature anomaly. This could be due to global circulation pattern changes. And this has an effect on precipitation, the supply side of moisture from the atmosphere, and evapotranspiration, which is the demand side to the atmosphere. And this can occur over a few days or weeks. And this is what we typically call a meteorological drought. And you can see here evapotranspiration has a defining role as a key indicator. Now, if this situation persists over several weeks, months, or years, this has an impact on soil moisture levels, and this ultimately can stress crops or forage in terms of livestock and reduced yield. And this is what we call an agricultural drought. And as an agronomist, this is really what we're interested in. Now, if we look at longer timescales, then we start talking about hydrologic droughts, so impacts on flows, groundwater, and above ground or overland flow. And then ultimately the broadest time scale is socioeconomic drought. So basically, you can see why ET is important in terms of how we define drought. So historically, and I point you to this paper here, hopefully Agnieszka and Jennifer can provide you with a copy of the presentation, but I have citations here at the end, West 2019, who gives a nice historical overview of drought monitoring with remote sensing data. And we can see traditionally, we used weather stations to derive meteorological indices, mostly precipitation-based, to identify when a drought starts, the trigger, the duration, magnitude, etc. However, in the 1970s, with the launch of Landsat, and then on through the 80s, 90s, and 2000s, we start seeing a number of vegetation-based approaches, and that's just because we had this higher spatial resolution data, multispectral broadband data, and so now you start seeing the normalized difference vegetation index, EVI, and now there's a whole bunch of indices that people are exploring for drought monitoring. And also in the West paper, he provides this nice figure that shows basically the proportion of drought, let's say drought monitoring indicators that have been analyzed in studies. And you can see here, NDVI takes the lion's share of indices, namely the Vegetation Health Index is widely used. It's a combination of NDVI and land surface temperature. But here in the small little blue box, you see the Evaporative Stress Index, which is probably the most popular evapotranspiration-based index for drought monitoring. And it's particularly powerful because it can track what are called flash droughts. And these droughts are becoming more frequent in dryland areas in Africa and elsewhere. And basically what happens is you could have ample rainfall as indicated by a rainfall-based or precipitation-based index, but the temperatures are so high and the atmospheric demand for moisture, what we call the potential evapotranspiration, is so high that the water evaporates before it's any use to the plants, right? And that's why ESI has become so powerful, because it captures that demand side and then you see the real water usage by the land surface. And this is the formula. I am a physicist, so I do know big, scary equations, but I try to keep it simple in my presentation. So ESI is simply the ratio of evapotranspiration. That's the water evaporated from the soil or transpired from the roots of a plant through its stomata to the atmosphere. That combination, also water evaporated from the plant surface. That's your evapotranspiration. You sometimes see it called actual evapotranspiration. And it's the ratio to this atmospheric moisture demand, which is PET. So obviously, as evapotranspiration increases, or the demand for atmospheric moisture decreases, then ESI approaches 1. And then conversely, yeah, if ET decreases, PET increases, then ESI approaches 0, which is bad. So evapotranspiration historically is measured in mass units, millimeters, or meters cubed. And to a remote sensor, that's not probably the most useful unit. So we luckily have this convenient way of converting mass units to energy units. And so you oftentimes see this term latent heat used instead of evapotranspiration. And it's essentially the energy equivalent of evapotranspiration. And you probably remember these phase transition diagrams from high school chemistry, but I think it's a nice way of illustrating the relationship between the two. So if you can think maybe of water, ice, frozen, solid state, if you apply energy, heat energy to that substance, the temperature increases, and basically you eventually reach this kind of phase transition, which is illustrated on the chart here. It's melting. Similarly, you have one from liquid to gas as well. And a way I like to visualize this is when you're making pasta and you're boiling water. I feel like, but I could just be crazy. I am from California. We have weird ideas sometimes. I almost see the phase transition. So when you're boiling the water, you see the water jiggling, and then at some point it starts to boil. But I feel like there's this kind of pause, and I like to think of that as the sort of phase transition. So with evapotranspiration, of course, you're not adding that kind of energy to the system, but you are increasing temperatures, and so there is this vaporization of water, the liquid to gaseous state, and there's this convenient relationship here. Uh, Basically, at 20 degrees Celsius, you need approximately 2.45 megajoules per kilogram to vaporize 1 kilogram of water, and then we express this in this kind of funny unit, millimeters, which is a length, but it's actually a volumetric measure. And so you can see how the two are interrelated. Okay, so now we're talking energy. Now, and so now I think we can dive into the remote sensing part. For most of you, I'm sure you have a lot of knowledge on ecostress, probably more than me. But anyway, I included the slide just so you can see the motivation for looking at land surface temperature. So ecostress produces these level 3 products, namely evapotranspiration and the evaporative stress index. And ecostress captures land surface temperature, which you can see here in Southern California, where I'm from. And so what now is the link between land surface temperature and this latent heat of evapotranspiration, or latent heat of vaporization? So we have to have a quick review of the surface energy balance in order to understand this relationship. And then we'll get into probably things you're more knowledgeable about. So in terms of the surface energy balance, we have this schematic here: net radiation, which is typically acquired from ground instrumentation at equivariance flux towers, or is available in gridded climate reanalysis data, ERA5 land, for example, is basically the sum of latent heat, that's your evapotranspiration, soil heat, and sensible heat, which is the heat basically that you feel. So when you touch your skin, that's latent heat. When you sweat and you cool down, that's basically latent heat. Those are I think a good way to visualize the differences. So net radiation is, of course, a combination of uh, various shortwave and longwave radiation. Shortwave radiation coming from the sun, interacting with cloud or the surface, and then radiation is radiated at longer wavelengths and can be re-radiated by the cloud. So all of this together is your net radiation, and it's the sum of these three components. So the energy balance approach does not estimate latent heat directly. And that's why sometimes people call it a residual approach. What it actually is estimating is this sensible heat. And the reason being is because I think historically sensible heat was easier to measure, had less uncertainty, and so this was the focus. Also, maybe the physics was better understood. So you see basically with these energy balance approaches, they're estimating sensible heat. And the idea is there's this sort of trade-off: as sensible heat increases, latent heat decreases, and vice versa. And so if you know sensible heat and you know the net radiation, soil heat flux is either assumed zero on timescales of monthly or coarser timescales, which is reasonable, or at finer resolution, say daily. It's usually a function of sensible heat or latent heat or net radiation, right? So basically, this is what we're relying on when we develop evapotranspiration models. We look at the sensible heat. So now I'd like to just give you a fun question. This will be interactive, so you'll use Mentimeter. I'll show you the slide for that, and then we can see what the results are. So please have your laptop or your cell phone ready, mobile, I guess we call them these days. And this is the question, just to see if you understand latent and sensible heat. Some of you may know that there's actually a famous movie, a beautiful movie, about the rabbit fence. There are a number of them actually in Australia, but these fences span large portions of the country. You can see from this Google image actually a demarcation of the rabbit fence. The green area in the southwest of Australia is irrigated cropland, and the interior is sparse vegetation, dry, and it's demarcated with this rabbit fence. And the idea of the rabbit fence is to keep rabbits from moving from the dry area to eat all the delicious food on the green side. And in this very famous experiment in 1993, they actually saw that thunderstorm activity, which you can see here, this beautiful cumulonimbus cloud, was much higher on the dry side of the fence than the wetter, sort of more lush, irrigated side. And so this is a nice chart that I think illustrates it. You can see here on the x-axis, this is the distance from the rabbit fence in kilometers, and you can see the agricultural area, the lush area versus the sparsely vegetated area is clearly demarcated. And then you also have the heat flux for sensible heat, the solid line here, and the dotted line. Right, so I just want you to observe the patterns in sensible and latent heat for the wet, vegetated, irrigated side versus the drier, sparsely vegetated side. All right, so my question is for you all, and you can use this Menti code. You can go to menti.com and type in this code, 83291683, to answer the question, why is there more thunderstorm activity on the drier side? Is it because latent heat is much higher on the drier side? Sensible heat is much higher on the drier side. Sensible heat is much higher on the wetter side. Land cover has no impact. So let's see if I can do this. Yes. So you can see the code here again, 83291683. And if you can just enter your response, then we should see in almost near real time your answers. Yeah. Okay. Impacts. So there's a mix of responses. This gives me hope. After I saw Martin's talk, I was like, oh, I hope this isn't. I didn't know exactly the level of the audience, so I tried to keep it simple. So I hope this is interesting to you all. And it looks like, at least for a few of you, it's useful. Okay, so I think we can conclude. Does anyone want to brave why they chose latent heat is much higher on the drier side? The one person? Why they chose that answer?
Anyone brave enough? We're looking for candidates. Yes, okay, wait. Candidate. Wait, I'm coming to you.
Updrafts?
Michael, can you hear us?
I heard something first.
Yeah. Basically, more convection and updrafts. So vertical development of cumulus clouds.
Yes, but would that happen from an increase in latent heat or sensible heat? Do you think that's the process for sure? But what's triggering it? What's driving it? Do you think?
Anybody? Sorry, Michael, I think you need to give us the answers.
Yeah, no problem. Yeah, no, it's this question I think is important because it really fundamentally helps you to understand why these energy balance approaches work. And so, like I said, there's this trade-off between sensible heat and latent heat. And what we typically find is vegetated areas have higher latent heat, Another way of visualizing it is, I'm sure for many of you, you walked barefoot without shoes when you were kids, and you would, in the summertime, you would walk on the pavement, it would be quite hot. And then what would you do? You would jump to grass because it was cool and wet, and that's that latent heat, right? So vegetative areas tend to have more latent heat, bare areas have more sensible heat. And so this trade-off is essential to understanding the surface energy balance approach to ET. So the correct answer is the second one, sensible heat is much higher, and that's because vegetation is sparse or low, and this heat is actually driving the convection, right? Okay, so, sorry, I'm trying to manage okay, here we go. Winter, great. Okay, so maybe now we enter more of your comfort zone. Again, for most of you, it's probably review, but it helps me to tell the story of why we look at sensible heat and use land surface temperature. So it works on this basic principle here, Wien's displacement law for black bodies. You can see it illustrated here. This is radiance on the y-axis and the wavelength in nanometers on the x-axis. And these are black body curves for various surfaces of different temperatures. And so the idea with Wien's law is that hotter objects emit energy at shorter wavelengths, higher frequencies. So this is why the sun is actually more greenish, but let's just say yellow-green. And then the human body, which is much colder, emits at much longer, lower energy wavelengths in the thermal infrared. And so this is an illustration of this, which you may have seen in an airport or some sci-fi movie, Total Recall or something. Yeah. So basically, we use this relationship then to relate radiance to temperature. And as Martin showed in his presentation, this is expressed in functional form, Planck's radiance function. You can see expressed here. This is radiance B as a function of temperature T in Kelvin. And then if you invert the PRF, you get your temperature in terms of radiance. And then with a few modifications, you have these sensor-specific coefficients, which you can retrieve from the metafiles. And this basically gives you temperature. You can use it to estimate land surface temperature or top of atmosphere temperature. And so this slide shows top of atmosphere brightness temperature. And that's again just to tell the story. Once you have this top of atmosphere brightness temperature, you have to convert it to land surface temperature. And of course, we have to do some atmospheric correction in order to bring it to that level. And so this is just another illustration here. We convert the radiance temperature, the land surface radiance to land surface temperature by making this kind of atmospheric correction where we account for atmospheric transmission, which I highlight here in the blue square, and the upwelling and downwelling long wave radiation. This is a nice tool, by the way. It doesn't work anymore, unfortunately, but it produces these measurements anywhere in the globe. It's from a 100 by 100 kilometer climate reanalysis grid, but unfortunately it doesn't work anymore. Anyway, so now basically we have the land surface radiance atmospherically corrected, and we could go back then and use this function to convert to land surface temperature. So again, for many of you, I'm sure this is nothing new. So now, what do we use land surface temperature for in terms of estimating sensible heat and ultimately latent heat or evapotranspiration? And so we use this basic relationship here, and there are different ways of doing it, and that's how the different models have emerged. And so basically, sensible heat is a function of land surface temperature, T sub 0, and atmospheric temperature, T. So obviously, as the land surface temperature increases, there's more sensible heat. And you also have this atmospheric resistance term, which is actually a major source of model uncertainty. And this is one of the reasons why we have so many different models, which basically adjust for the sensible heat. And then you can see here, yeah, typically we estimate land surface temperature with Aster or Landsat and EcoStress in the case of our project. Now, the typical way EcoStress uses models evapotranspiration ESI is not with this general method of surface energy balance. And that's why I include this slide here, because you can see highlighted here, these three models stick, which I don't know so well. TSEB and SEBS I know much better. These are surface energy balance approaches, and this is the approach the European EcoStress Hub has decided to take to measure ET, estimate ET and ESI. Right? So let's dive in a little bit more on how this function of sensible heat and land surface temperature is used in different models. And I've tried to organize them into four general categories, namely empirical methods, which I don't talk about so much because they're not very widely used. They have issues, as most empirical models, of transferability. Single source models like Siebel, metric, and SEBS, these are really represent the lion's share of evapotranspiration models that use land surface temperature. Scatter plot methods, not also very widely used, but nice to understand basic concepts. And one of the reasons is this has to be done sort of manually. And then, of course, the Cadillac or the Mercedes of models. These are the two source models like TSEB and Alexi. But of course, these have some problems in terms of operationalization. They're incredibly complex. And in the end, their performance is not very much better, even when driven with high quality data, than these single source models. So these are some of the major uncertainties of surface energy balance models. So this estimation of land surface temperature and atmospheric temperature is difficult, and as many of you know, thermal experts, land surface temperature is sensitive to atmospheric water vapor. The surface is not a perfect black body, it's heterogeneous, and so this wreaks havoc on the emissivity of the surface. Atmospheric correction also is needed and is not perfect. And so, but I would say probably the biggest problem is with this transport coefficient for the atmosphere, and it's because it's highly sensitive to changes even on a sub-daily time step. Wind, temperature, humidity, you name it. And then another issue is this one-time overpass. So historically, these models use Landsat, which is available every 16 days. And on that day, they estimated what's called the evaporative fraction. And then they use that to sort of extrapolate over the other days, daily evapotranspiration. Of course, there's issues with that as well. It is, in fact, constant over the days that we don't have satellite observations. So probably the most famous, I would say, empirical method is this one by Wang, 2007, and it simply estimates latent heat as a function of net radiation, vegetation index, and land surface temperature. But I've never seen it used anywhere, so I'm assuming, like most empirical methods, it has that transferability issue. So I'll focus mostly on these three, which are the most commonly used. And they each uniquely address uncertainties in the SEB approach to estimating sensible heat latent heat. So the single source methods, Siebel is probably the most common. Metric is a commercial version, basically, of Siebel. And what it does is it uses pixels within an image to sort of calibrate this difference between land surface temperature and air temperature. And I show a nice illustration here of that process. So you can see there's basically a sort of wet extreme, a very vegetated surface within a pixel, and a very dry or bare soil or urban extreme also in the same image, ideally. And it uses these extreme pixels to calibrate the LST air temperature difference. And so we see here this Landsat false color composite. The red blob here could be a forest or some other dense vegetation. And so it appears red because it's basically has a high NDVI due to chlorophyll absorption in the red and near-infrared radiation scatter due to the structure of the canopy. In the land surface temperature region of the spectrum, you see it's a cold pixel, and that's because it's dominated by latent heat. So latent heat basically is approaching net radiation because your sensible heat is approaching zero. So this is what is called the wet or cold pixel. Conversely, you have this is an urban surface, it's grayish white, and so it's dominated by sensible heat, H. Latent heat is zero. And so basically your sensible heat is simply a function of net radiation. This time you have to include the soil heat flux component. And you can see it's our hot or dry pixel. It's very warm in the thermal infrared. And then of course, NDVI, it's almost black. And so, yeah, that's basically how the single source approach works. Scatter plot method is another method, but it's done by actually plotting land surface temperature pixels versus NDVI pixels. You can see it illustrated here. And depending on how you standardize the data, that affects the shape. So the triangle method is the most common, but there's also the trapezoid method. But I show the triangle method here because it was the first proposed by Moran in 1994. And so this is a nice visual of that trade-off between sensible heat and latent heat, land surface temperature, and NDVI. So you can see here your kind of wet pixel on this vertices. So NDVI is very high, land surface temperature is very low. And then conversely, your dry pixel, right? NDVI is very low, land surface temperature is very high. And between these vertices, you have basically bare soil, partial cover or full cover, vegetative cover. And you can see it kind of visually here. These are some dry rice fields, probably in Southeast Asia. And you can see the bare soil, very high land surface temperature, and the bluish, colder areas, this is vegetated, right? So you basically would look at this image, but in feature space here on a 2D plot, basically. And you would draw it, and then you could use that then to calibrate this land surface and air temperature difference. So the most sophisticated models are these two-source models. They work in a number of ways, but essentially vegetation and soil are estimated differently. The vegetation side is estimated using a vegetation index approach, which I'll talk about in the subsequent slides. In this case, Penman-Monteith. Some use Priestley-Taylor. And then the soil component is estimated in much the same way as single source models, but only for soil, basically. And then I only mentioned Martha's dyslexia here. This is quite cool because Alexia was her first model, which was based on Norman's 1995 model with Bill Kustis, I believe. And then basically she uses the Alexia model and Landsat thermal infrared to downscale. And that's what the dyslexia approach is. And I have a paper here, Norman's 1995 paper. From there, you can see how the science has evolved. Okay, so this surface energy balance SEBS approaches, like I said, these are the most commonly used with thermal infrared to estimate ET. This is also the approach the European Ecostress Hub has decided to take. However, there's a number of other different ways to estimate ET, namely this empirical crop coefficient approach. This is Allen's original approach, FAO 56. And this is, I would say, kind of a semi-empirical approach. You also have the direct evapotranspiration approaches, Priestley-Taylor JPL. So I mentioned this one here because this is the one actually EcoStress originally used to derive its level 3 products. And it's similar, but I would say arguably much better than the Mod 16 product, ET product, which is Moo's model. And these do not use thermal directly. They are mainly driven by vegetation indices. However, there have been a few studies that have tried to integrate thermal infrared using ATI, the apparent thermal inertia, on the soil component, which I can talk about briefly in the subsequent slide. And then you have this whole other class. So these are energy balance approaches. This is water balance approaches, which I don't know so well, but these are SAVAT models, land surface models that focus on the mass side of the equation. And you do see now models that try to couple the two processes. So this is a schematic of the Priestley-Taylor JPL model. This is actually the model I used for my dissertation at UC Santa Barbara. And it's basically the canopy component of latent heat and the soil component, also the water intercepted and evaporated by the surface. But in dryland areas, we usually assume that's zero. Intercepted moisture is usually high in like dense humid forests. So I tend to omit it. It also makes calibration much easier. And this canopy component is driven by the chlorophyll containing portion of the canopy, F sub G, or green canopy fraction, which is derived from EVI because EVI is much more sensitive to chlorophyll content. And then the overall absorption of the canopy of energy, which is estimated with this normalized difference vegetation index. You also have your net radiation and an air temperature constraint. And the one where thermal has shown some value is with this soil moisture constraint, because traditionally the soil moisture constraint is estimated with the vapor pressure deficit. You can think of it as kind of relative humidity. And the idea is based on Boucher's complementary hypothesis that as a surface becomes wetter, it tends to humidify the air above it. So basically, air humidity is indicative of soil moisture content. Now, in a humid area, that might work well, but in dry areas, this is horrible, right? So we've done some work using thermal, but also radar, Sentinel-1, to see if we can improve our estimates of soil moisture, which we can. So, so when I started looking into EcoStress and writing the proposal, actually, I thought this is how it would integrate thermal, but it doesn't. You can find out more here. This is the NASA link to EcoStress and PT-JPL. It actually uses thermal in the net radiation component. So it still uses this vapor pressure deficit. And they argue in the ATBD that they look at the net radiation side because land surface temperature plays a much more important role than on the soil moisture fraction. I don't know how true that is. I can't say one way or the other, but I think they did some preliminary analyses, and this is what they showed. So basically, land surface temperature is used on the long wave upwelling component of the net radiation equation. So if you recall, that's a function of emissivity, right? And that's where the land surface temperature goes, basically. And this is what Agnieszka's been helping with us with brilliantly on the project. So if you'd like to know more about the PT-JPL model, Josh Fisher's 2008 paper is quite a good place to start. So in conclusion, thermal infrared is widely used for evapotranspiration. Estimation in agronomy in my field is usually used for drought monitoring and irrigated agriculture planning and management. Evapotranspiration is unique because it is not only a primary component of the surface balance, energy balance, it's also linked to the water balance, both in the atmosphere and on the surface. SEB models are all basically relying on this trade-off between, let's say, land surface temperature, which is indicative of sensible heat, and NDVI, which is indicative of latent heat. And essentially warmer, drier surfaces, bare soil, urban, tend to radiate more sensible heat, leading to less latent heat, and cooler, wetter surfaces, vegetated surfaces, conversely emit more latent heat and less sensible heat. And I would say because EcoStress uses this PTJPL approach, we have compared it to the TSEP approach, and actually it does even the original model does better than TSEP in dryland areas, particularly when driven with hyperspectral remote sensing. So if you're looking at perhaps estimating evapotranspiration using thermal infrared, I would probably look into these non-thermal approaches and looking at ways you can integrate land surface temperature as EcoStress did in combination with hyperspectral. I think that's something I'm interested in also exploring in the future. So I'd love to talk to you all about that. Maybe not here, but you can always email me. And I think with that, I probably went way over. But yeah, I'm open to questions, comments.